Okay, so hopefully this shows up. I think we have it on screen here. So in our program, we set up the probabilities the other way from the way we talked about in the video. So dad winning is 60% in our example here, and champ winning is 80%.
Yep.
Sorry, I don't need to print those at the end. It'll shrink. Chance. And then we run 1,000 trials. And each one of our trials is we just pick a random number for each game A, B, and C. And then if A is bigger than the champ win number, so if I get 0.9 here.
The number's between 0 and 1.
Yeah, random real is a random number between 0 and 1. So if I get 0.9 bigger than the champ wins probability, what would that mean?
So it means he wins.
Right, the kid won. And B is greater than dad win if the random number is bigger than 0.6, then dad wins. So what we're doing here in game A, playing the champ, B playing the dad, and C playing the champ. Then what I do is I increase my count. Oh, and there's a little bit of programming notation here. You see, I have to be greater than the champ and greater than the dad together.
Mm-hmm.
These double vertical lines mean or. B is greater than dad and C is greater than champ. So if either I win the first two or I win the second two, I increase the count.
Okay.
Okay. So in this case, for 1,000 trials, looks like this way was about 14.8, but we can increase it to 100,000 trials, so 14.5, or even if we wanted to do 1,000,000 trials, just to be sure. 14.3. So we're getting pretty consistent numbers there.
Mm-hmm.
So
He's winning like around 14.5% of the time.
yeah, or the 1,000,000 times it was 14.3.
Mm-hmm.
So now, how can I make it the other way around? Dad, champ, dad.
So we just
You just
switch dad and champ here.
Okay.
and in the other set too.
Okay. Dad win, champ win,
Yep.
and then champ win, and then dad win.
So this should be a larger probability.
Now we're playing the champion in the middle.
Actually, no, this should be the smaller probability. This is the second case.
With 1,000, it was 12.3. With 100,000, 12.8. Run it again with 100,000, I'm getting 12.88. And with 1,000,000, let's see what I'm getting.
12.7. So it is a lesser probability.
It's significantly less.
Okay, cool. So now let's put in the probabilities that we did in our example. So the dad win was a half, and in this case, the champ win, we want it to be a third.
Mm-hmm.
So, but we were beating the champion a third of the time.
So it's 2/3.
So in the way we've written the program, the champ win is 0.666, or I could make it even, all the way out.
Mm-hmm.
Okay. So with 1,000,000 trials here,
The kid wins about a quarter of the time.
okay, and then if I reverse it, we expect more wins, right?
Yep.
Wait, a quarter of the time? Oh yeah, that's what we got, right? And then we should be getting 5/18ths in the second time?
Yeah.
Champ win, dad win.
But I think this is bigger than a quarter.
Alright, again with 1,000,000 trials. So we get 0.277444. And maybe do I have room on the screen? Yeah, so let's take our output and times it by 18 divided by 5. See if that was approximately 5/18ths.
And we get,
And we get
yeah.
0.998. So let's just do that one more time. So we can see we did the calculation, or that our simulation replicates our calculation. So it must be that 5/18ths is about 0.278.
Yeah, here we're a bit bigger.
Looks like it is.
Slightly bigger.
Yeah, and then just for giggles, n of 5/18ths to say 10 decimal places. 0.2777.
Right.
Right, so is this a surprise?
A Well, yeah, I think it originally, what I thought the first setup, dad, champion, dad, would have a higher probability because the dad's an overall worse player and you're playing him more.
Mm-hmm.
But it turns out if you play the dad in the middle, then it's easier for you to win 2 games in a row.
What do you think?
Yeah, it's a surprise because I thought it would be the same because you have to play the same 2 sets of games, just in different orders. But apparently, the who you play first does make a difference.
Cool. All right. Good job, guys.